Hello, welcome to the second module on the course on application of spectroscopic methods in molecular structure determination. In this module, we will consider nuclear magnetic resonance spectroscopy or the NMR spectroscopy. We will consider the basic principle behind this particular spectroscopic technique. Nuclear magnetic resonance spectroscopy is a very powerful tool. It is very widely used in the structure elucidation problem of organic, organometallic, and inorganic complexes. It is an indispensable tool in the chemistry laboratory. Whenever a student makes a compound, a new compound, immediately rushes into the nuclear magnetic resonance spectroscopy laboratory to record the NMR spectrum. The wealth of information that one gets from the NMR spectrum is invaluable in structure solving problems. Now, from the historical perspective, the phenomenon of nuclear magnetic resonance was discovered in the year 1945 by two groups working independently, one at the Harvard University and another at the Stanford University. Purcell, Torrey and Pound, they were working at Harvard University. Bloch, Hansen and Packard were working in the Stanford University. The experiment they performed was very simple. They placed a sample of ethyl alcohol between pole pieces of an electromagnet and irradiated the sample with electromagnetic radiation. What they observed was that the sample absorbed the electromagnetic radiation in the radio frequency region when the magnet was turned on. When the magnet was turned off, there was no absorption of the electromagnetic radiation. From this experiment, they concluded that they are actually studying a magnetic property of the sample. Purcell and Bloch were awarded the Nobel Prize in Physics in 1952 for the discovery of the NMR phenomenon. Now, NMR phenomenon was developed into NMR spectroscopy and now it is very widely used for the structure determination. Now, here is the very first spectrum of ethyl alcohol published using a 30 MHz NMR spectrometer corresponding to roughly 0.7 Tesla of magnetic field strength. This is a very unresolved spectrum in today's standards. Nevertheless, from the historic perspective, it is a very important discovery. Now, when you look at the spectrum, you see three different peaks in the NMR spectrum. And if you look at the structure of ethyl alcohol, there is a CH3 group, there is a CH2 group, and a OH group. So, one can assign these three peaks corresponding to one for the CH3, that is this particular peak here, and one for the CH2, which is this particular peak here, and one for the OH. In fact, if one measures the area under these three peaks, it will correspond to 3:2:1 corresponding to the CH3, CH2 and OH. So much of wealth of information was available right at the first instance of recording the very first NMR spectrum of ethyl alcohol sample. Now, let us look into some properties of the nucleus in terms of what is useful for nuclear magnetic resonance spectroscopy. Now, we are dealing with the magnetic properties of the atomic nuclei as evident from the NMR experiment. Atomic nucleus has both mass and it also spins on its own axis. Because of a spinning mass, it has an angular momentum. Because of a spinning charge, it also possesses magnetic momentum. And these two parameters are essential parameters for the NMR experiment. The angular momentum is given the symbol P and the nuclear magnetic momentum is given the symbol nu. Only certain nuclei have non-zero magnetic moment. In other words, net magnetic moment can also be zero in certain other nuclei. Only nuclei with non-zero magnetic moment are magnetically active, and those are the nuclei which are useful for the purpose of nuclear magnetic resonance spectroscopy. In other words, those nuclei whose magnetic momentum is zero cannot be useful or is not useful for the purpose of nuclear magnetic resonance spectroscopy. Both these quantities, namely the angular momentum and the magnetic momentum, are vector quantities, and according to quantum chemistry, they are quantized in nature. The ratio of the magnetic momentum to the angular momentum is what is referred to as the gyromagnetic ratio. Gyromagnetic ratio is a fundamental constant of a nucleus. It is a constant for a given nucleus. The ratio, namely nu by P, is called gamma, which is the gyromagnetic ratio. This is an important parameter in the case of nuclear magnetic resonance spectroscopy. Now, let us look into certain resources that are available in the internet In the internet, there are quite a lot of resources available as far as nuclear magnetic resonance spectroscopy is concerned. I am highlighting two such examples in this particular lecture. The first one is from this particular website. When you go to this website, it gives you an interactive periodic table. In the interactive periodic table, if you click on any particular element and look at on the left hand side this particular bar here, it tells you very valuable information regarding the parameters that are useful for the nuclear magnetic resonance spectroscopy. It tells you the spin of the particular nucleus, the natural abundance, its availability in nature, for example, the frequency factor, the gyromagnetic ratio, and so many other parameters are listed on the left hand side bar of this particular slide. Now if you go to another website, this is by the company Bruker, which manufactures the nuclear magnetic resonance spectrometers. This is also an interactive periodic table. If you click on any particular element, then the screen pops up with the information that is relevant to the NMR experiment. For example, it lists all the isotopes that are magnetically active, their natural abundance. In cases where the isotope is a synthetic isotope, of course, the natural abundance will be 0. The nuclear spin, the gyromagnetic ratio, if there is a quadrupole moment, it also lists the quadrupole moment. It also tells you the resonance frequency with reference to proton being a 500 megahertz resonance frequency. It also tells you about the sensitivity with reference to proton as a source. These are kind of information which are very useful. So one can identify in the periodic table what are the various elements that are present in terms of its property related to nuclear magnetic resonance. Now we'll deal with the very basic theory, non-mathematical way of describing the theory of NMR spectroscopy. Nucleus should have a non-zero magnetic moment. In other words, it should be magnetically active, first of all, for the experiment to be considered for the NMR spectroscopy. According to quantum chemistry, angular momentum can have only certain fixed values, which are given by P is equal to m divided by h by 2 pi, where m is the magnetic quantum number of the nucleus. Now the magnetic quantum number can have, in the presence of an external magnetic field, different values corresponding to 2i plus 1 values, namely plus I minus 1, I minus 2 all the way to minus I, where I is the spin quantum number of the nucleus. For example, if you consider I is equal to half, then the number of spin quantum, the allowed orientation of spin angular momentum I in an external magnetic field is what is described here. For a spin of half, you can have a possibility of plus half and minus half. For a spin of 1, for example, you can have the possibility of plus 1, 0 and minus 1 in accordance with this particular rule, which tells you the number of magnetic quantum numbers that are possible in the presence of an external magnetic field. Now for a spin of 3 by 2, you can have 3 by 2 plus half, minus half and minus 3 by 2. Pictorially, it is represented in this particular format. If this is the direction of the applied magnetic field, then a spin half nucleus can have two spin states, namely minus half spin state, which is the ground state, and plus half spin state, which is the excited state. In the case of a spin 1 nucleus, it can have three different orientation or three different values. The minus 1 state is the ground state. Then you have the first excited state, which is a 0 state, and the plus 1 state, which is the higher excited state. Now quantization of spin angular momentum is what we are talking about in this particular case in the presence of an external magnetic field. This is what is known as the Zeeman splitting in the NMR terminology. Now there is an easy way to find out what is the nuclear spin of a given nucleus. This is called the odd even rule. This is a highly empirical rule. It has no basis in terms of theoretical basis or anything. It is a very mnemonic kind of methodology to determine the spin of a given nucleus. This is purely based on atomic mass and atomic number. When the atomic mass and atomic number are even, the spin is always 0. When the atomic mass is even and the atomic number is odd, the spin will be a multiple of 1. And when the atomic mass is odd and atomic number is either even or odd, then the spin will be a multiple of half. The examples are shown here. For example, a spin of 0 would correspond to a carbon 12 nucleus, the isotope 12 of carbon, isotope 16 of oxygen, for example, they all have net magnetization of 0 and they are not very useful in the NMR experiment. When I is equal to integer, the examples are nitrogen 14, for example, it has a spin of 1, boron 10, for example, has a spin of 3, and deuterium has a spin of 1. The half integer nuclei is very useful nuclei, and this is what we would be considering for the rest of the lecture in this particular course. Proton has a spin half. Carbon 13, although it is a low abundant isotope of the carbon, it has a spin half. Nitrogen 15 has a spin half. Oxygen 17 has a spin of 5 by 2. Boron 11, for example, has a spin of 3 by 2. So this is a very simple methodology to find out what is the spin of a nucleus based on the odd even rule of the atomic mass and atomic number. Here we list some interesting properties of common NMR nuclei, for example, proton, deuterium, carbon 13, fluorine 19, phosphorus 31, and silicon 29. These are the most widely often used nuclei as far as the NMR experiments are concerned. Most of them are spin half nuclei with the exception of deuterium, which has a spin of 1. The gamma, which is the gyromagnetic ratio, is mentioned here, and the gyromagnetic ratio is a measure of the sensitivity of the nucleus as far as the NMR experiment is concerned. Higher the value of the gyromagnetic ratio, the more sensitive the nucleus would be. For example, if you take proton, which has a gyromagnetic ratio of 26.7 with a natural abundance of 99.9%, and consider fluorine, which has a very similar gyromagnetic ratio, roughly 25 or so, with a natural abundance of 100%. These two nuclei will have similar sensitivity in terms of the NMR experiment for two reasons. One, the gyromagnetic ratio is nearly the same, and secondly, the natural abundance is 100%, which is also nearly same, for example, for these two nuclei. On the other hand, if you take carbon and proton, carbon has roughly 1/4 of the gyromagnetic ratio, and it is not bad actually that it's only 1/4, but what is even worse is the natural abundance. It is about 1% is the magnetically active isotope of carbon, namely carbon 13. The remaining 99%, of course, is the carbon 12, which is not useful for the purpose of NMR experiment. So both the gyromagnetic ratio as well as the natural abundance play a very vital role in terms of the sensitivity of that particular nucleus for the NMR experiment. From now on, we will devote ourselves to the NMR of spin half nuclei, namely the proton and the carbon 13. In the absence of an external magnetic field, the magnetic moment vectors will be randomly oriented. However, in the presence of an external magnetic field, according to quantum mechanics, they will have finite values. They take up two orientations, which are conventionally represented as plus half and minus half. The two orientations corresponds to one aligning with the external magnetic field, namely minus half, another one opposing the external magnetic field, which is plus half, and they differ in energy. The energy difference depends on the strength of the applied magnetic field. This is diagrammatically represented in this particular slide. If you look at the side where there is no magnetic field, the magnetic field is applied here onwards, and in this side there is no magnetic field. In the absence of a magnetic field, the magnetic moment vectors, which are represented by these arrows, are randomly oriented. As soon as the magnetic field is applied, energy level is set up, for example, for the ground state and the excited spin states, the two states that corresponds to the minus half and the plus half state of the spin of the nucleus. And this energy gap is essentially corresponding to h nu, and you can see certain population in the ground state and certain population in the excited state. Now, this is the equation that governs the basic NMR experiment. This frequency or this energy gap essentially is directly proportional to the applied magnetic field. It is also directly proportional to the gamma, which is the gyromagnetic ratio. So these are the two parameters on which this energy gap, in other words, the energy separation between the ground state and the excited state, depend upon. The equation is simplified. In other words, the nu, which is the resonance frequency, corresponds to B0, which is the applied magnetic field, and the gamma, which is the gyromagnetic ratio of the given nucleus. So from this equation you can easily figure out that for every nucleus where the gamma is different, the frequency will be different for a given magnetic field strength. In other words, two nuclei which have different gamma values will resonate at two different frequencies under the same identical magnetic field strength. In other words, there are no two nuclei which will resonate at the same frequency under a given nuclear magnetic under the magnetic field given magnetic field strength, because the gamma is going to be different for the two nuclei. You can also see from this figure, as the field strength increases, this is an increasing field strength of the magnetic field. As the field strength increases, the energy also increases, the energy gap also increases, essentially indicating that this is directly proportional to the frequency, or the energy is directly proportional to the field strength. So with increasing field strength, of course, the energy gap also keeps increasing. The resonance condition essentially corresponds to matching this frequency to this particular expression. When the energy corresponds to the electromagnetic radiation, which corresponds to the expression here, is satisfied, then the resonance occurs. In other words, absorption of energy will take place. This is typically, the energy gap is such that typically the frequency that is necessary for this transformation from the lower spin state to the upper spin state corresponds to the radio frequency region of the electromagnetic spectrum. Now once you set up the alpha and beta state, or the minus half and the plus half state, which is shown here, for example, this is the lower energy spin state and this is the higher energy spin state. Once you set up these energy levels, then one can easily calculate, using the Maxwell-Boltzmann distribution law, the population ratio between the excited state and the ground state, which is governed by the exponential to the minus delta E by kT, where K is the Boltzmann's constant and T is the temperature at which the population difference or the population ratio is calculated. The N alpha and beta is the population ratio of the excited state to the ground state of the two spin states that we are talking about. Now this table tells us the results from the calculation of the alpha beta state population ratio with respect to the magnetic field strength and the corresponding resonance frequency of the NMR spectrometer, and in terms of the energy gap between the alpha and the beta spin state, or the plus half and the minus half spin state, is shown in this particular column here. And essentially, when the information is plugged into the Maxwell-Boltzmann's distribution function, one gets the result of the excess population, or the population ratio to the alpha to the beta population ratio is shown here. As you can see here, NMR is not a very sensitive technique because both the states are equally populated. Only a very small fraction of the order of ppm is the excess population that is present in the ground state in comparison to the excited state. At around room temperature or so, which is about 17 degrees, the calculation temperature that is shown here. But what is important is, as you increase the field strength going from 2.35 Tesla magnet to about 7 Tesla magnet, in other words, from a 100 megahertz NMR spectrometer through a 300 megahertz NMR spectrometer, the population gradually increases, which means the sensitivity should also increase, because now you have more population in the ground state for it to be excited to the excited state spin state of the system. So essentially this tells us that with increasing frequency of the NMR spectrometer, because of the excess population being higher, the sensitivity also goes up. Now what is the effect of temperature? You can, for example, measure the NMR spectrum at minus 100, or you can measure it at plus 100. The NMR spectrometer can be cooled to, the probe can be cooled to minus 100 or plus 100, and the measurements can be made. Since the expression, the population difference or the population ratio is inversely proportional to the exponential of one temperature, it is also affects the population difference. At low temperature, you have a higher population compared to higher temperature where you have a lower population, for example, because of the inverse relationship of the population ratio to the temperature of the system. So it is advantageous to measure the NMR spectrum at a lower temperature compared to higher temperature. However, you can see here the advantage gained by this experiment is not so high. It is only about twice as much of sensitivity increase as in the higher temperature, for example. So one always opts for increasing the frequency of the spectrometer or going to the higher and higher resolution spectrometer where the sensitivity is also higher. So to conclude the earlier slide, we will say that higher the magnetic field strength, higher will be the sensitivity as well as resolution. We will come to the resolution part a little later. Let us for time being confine ourselves to the sensitivity part. The lower the temperature, the higher the sensitivity. In other words, a 500 MHz NMR instrument is more sensitive as well as more resolving than a 60 MHz NMR instrument. As I mentioned earlier, the energy gap between the spin states corresponds to the radio frequency region. So, application of radio frequency essentially causes the absorption of the same due to the excitation of the nuclear spins from the lower energy level to the upper energy level when the two energies match. In other words, the energy which is applied and the energy gap of the two spin states, and this is what is known as the resonance condition. And this resonance condition essentially is when the frequency matches the energy gap, the absorption of the energy takes place, and the spins which are in the lower spin state get excited to the higher spin state. In the classical description of NMR, one can think about a nucleus which is processing around the magnetic field that is being applied. In other words, the net magnetization of a sample is essentially the sum of all individual magnetic moments. The interaction of the magnetic field with nuclear magnetic moment induces the nuclear magnetic moment to process about the applied magnetic field with certain frequency called the Lamar frequency. This is better explained using a diagram. For example, this is a spinning nucleus spinning on its own axis. When an external magnetic field is applied in this direction, namely this B0 is the external applied magnetic field, it starts to process around the axis of the external magnetic field, and this precision frequency is what is known as the Larmor frequency. When the precision frequency and the applied radio frequency match each other, there is a spin flipping that takes place. In other words, the spin that is aligning with the external magnetic field flips to the spin which is opposed to the external magnetic field. In other words, the minus half state spin goes to the plus half state, or the alpha state goes to the beta state, as the case may be. Now, once the spins reach the excited state, they will have to come back to the ground state to attain the equilibrium population. This is essentially happening by two mechanisms. One is the spin lattice relaxation, where the excess energy is actually transferred out to the medium and the surroundings, which is the lattice in this particular case. Or it can also transfer the excess energy to another spin, which is known as the spin-spin relaxation. Essentially, these are the two mechanistic features by which an excited spin state can come back to the ground state in the case of NMR spectroscopy. Now, from the above equation, one infers that all hydrogen nuclei must come to the same frequency. For example, if we consider all the hydrogen nucleus in a molecule, gamma is essentially same for all of them, and the B0, which is the applied magnetic field, is also same. So, all the hydrogens in a molecule should essentially confine to a single frequency which is governed by this equation. But we know that this is not true, because different hydrogens in a molecule come under different frequencies. Hydrogens in different chemical environment give different resonance frequencies in the NMR. And for example, if you take the ethyl alcohol spectrum itself, we know the OH hydrogen comes at a different frequency compared to, for example, the CH2 hydrogen, which comes at a different frequency, and finally the CH3 hydrogens coming at a different frequency. In fact, if you look at the higher resolution NMR spectrum, it's not only that the three different frequencies are obtained, there is also certain spectral features which we call as multiplets creeps into the picture, which essentially gives us a valuable information regarding the structure of ethyl alcohol. We will consider the finer aspects of the spectrum of ethyl alcohol. We will introduce the concept of chemical shift, and we will also introduce the concept of spin-spin coupling in the next lecture. So, to summarize, in this particular lecture, we have looked at what is an NMR phenomenon, how the NMR spectroscopy was developed from that phenomenon, and what is the basic principle behind the NMR spectroscopy. These are the things that we have covered in this particular lecture. Thank you.